Hello and welcome back to this bonus video on L'Hopital's rule. In my original video of L'Hopital's rule, we evaluated limits that gave us the form 0 over 0 or infinity over infinity. What we will find with this is that these aren't super common, but all of these 5 other indeterminate forms can be manipulated to resemble one of these forms. So our first example will be 0 times infinity. And our example is the limit as x approaches infinity of x times ln of 1 plus 1 over x. And so you can see this will give us infinity, this will give us ln of 1, which is 0. We get infinity times 0. That's our first indeterminate form. So let's manipulate this to be the limit as x approaches 0 of ln 1 plus 1 over x divided by 1 over x. What this gives us is 0 over 0, which is an indeterminate form where we can directly use L'Hopital's rule. So let's use it. The derivative of ln of a function is just the prime of that function over the function. So that will be negative 1 over x squared divided by 1 plus 1 over x. And this is all going to be divided by the prime of 1 over x, which is negative 1 over x squared. These will, oh, I forgot my limit notation. What we have now, these negative 1 over x squares will cancel. We will get the limit as x approaches infinity for 1 over 1 plus 1 over x. This will become 0. We will get 1 over 1, which just gives us 1. Now, some of these examples might get a little long, so I might not go over all of them. I will go over a few, but most of them I'll just show you how we get to the 0 over 0 or infinity over infinity. So our next example includes this indeterminate form, infinity minus infinity. Now a lot of people might think this equals 0. It doesn't, because since infinity doesn't technically exist, and 2 times infinity, say, equals infinity, if we had 2 times infinity minus infinity, which is the same as infinity minus infinity, and let's say we factored infinity out as if it existed, we'd have 2 minus 1. Well, now we've got 1 times infinity, which is just infinity. But if we have infinity minus 2 times infinity, which should technically be the same thing, we get infinity times 1 minus 2, which is negative 1 times infinity, which is negative infinity. So that's why we can't have infinity minus infinity. Lots of infinities. It's like when you say a word so much that it starts to sound like it's not real. But let's get into our example. We have the limit as x approaches infinity for root x squared minus 2x minus 4 minus x. And this is going to give us infinity minus infinity. But with some easy manipulation, we can get a different answer. Some might think to maybe factor this but that's not actually the answer. I put that there to trick you guys. But what we can do, well, I guess you could still call this factoring. We're going to make this the limit as x approaches infinity for root x squared times root 1 minus 2 over x minus 4 over x squared minus x. We remember that root x squared equals absolute value of x, but since we are on the positive side of 0, positive infinity, this is just going to be x. So this is the limit as x approaches infinity for, let me just make this the x here. What we can do is factor out this x, but let's put it onto the bottom as a 1 over x squared. So we've got root 1 minus 2 over x minus 4 over x squared minus 1 over x. Now, you'll notice if we plug infinity in, this becomes 0, this becomes 0, root 1 becomes 1, minus 1 is 0, this becomes 0, that's 0 over 0. We can just derive this. Now, this would take some seriously not fun seriously not fun derivatives, but you can see that we could use it if we were trying to evaluate this limit. Let's move on to our next indeterminate form, 1 to the power of infinity. A lot of people might also think that this is 1, but since infinity technically does not exist, we can't say that it just equals 1. So our example is the limit as x approaches 0 from the positive of cos x to the power of 1 over x. What's this going to give us? Well, that's going to give us cos of 0, which is 1, to the power of the limit as x approaches 0 from the positive of 1 over x is infinity. That's 1 to the infinity. Now this is where these kind of get a bit complicated. What we're going to do is we're going to remember that e to the power of ln of any function is just the function. But we're going to keep in mind that ln of some function to the power of another function is that power function right in front of it. And so we're going to use this trick. We're going to take the limit as x approaches 0 from the positive of e to the power of ln of cos x to the 1 over x. What we can do is take this 1 over x out front. What that's going to be is 1 over x times ln cos x, which is also ln cos x divided by x. So that's what we have now. Let's keep in mind that since e is a constant, we can actually bring this limit up using our limit laws. And so therefore, we're going to have the limit as x approaches 0 of ln of cos of x divided by x. Well, what's cos of 0? That's 1. What's ln of 1? 0. That's 0 over 0. So we get e to the limit as x approaches 0 from the positive of ln cos x divided by x, which equals e to the 0 over 0. We could solve this. I'm not going to, because once again we're going to have a pretty long problem. It might be a little shorter than the last one, but it's still pretty long. And we can see how we would just derive both of these. the x would go away, we'd be completely fine. Let's move on to the next indeterminate form. We have infinity to the power of 0. Anything to the power of 0 is 1, right? Not always. Well, this isn't really going to prove it to us because, sorry to spoil it, but the answer is 1. But we have to prove why it's 1. So we have the limit as x approaches 0, infinity, of x to the power of 1 over x. What we're going to get is infinity to the power of 0. That's our indeterminate form. Let's use the trick we just used. This is equal to the limit as x approaches infinity of e to the ln of x to the power of 1 over x. You know, let's erase these as we go on so they're not getting in our way. And so we know how far we've come. Well, we can take this 1 over x out front and put it on the bottom. We get the limit as x approaches infinity for e to the ln x over x. This is e to the infinity over infinity, so we can use L'Hopital's rule on this here since e is a constant. So this equals e to the limit as x approaches infinity of ln x over x. Let's derive the top, let's derive the bottom. E to the limit as x approaches infinity for 1 over x divided by 1 equals e to the limit as x approaches infinity for 1 over x. That's an easy one. That's 0. E to the 0, and that's 1. It's not very exciting. It's what we expected. But we proved why it's 1. Last indeterminate form, 0 to the power of 0. I'm going to be honest, I'm not exactly sure why this form doesn't exist, because they always tell you I think I was in grade 7 maybe when they told me anything to the power of 0 is just 1. But we've seen 2 forms now where we can't. So, it also violates the 1 to the power of anything is just 1. But let's just hop into the example. Limit as x approaches 0 from the positive of x to the power of x. We can see immediately that's going to be 0 to the 0. So let's use our e to the ln strategy, I guess you could call it. This time I'm just going to take the limit up immediately because we know that we can do that. Let's take the x out front. We get e to the limit as x approaches 0 from the positive of x ln x. What do we get here? We get e to the limit as x approaches 0 from the positive of 1 over x under ln x. The limit as x approaches 0 from the positive of ln x is negative infinity. And for 1 over x, it's positive infinity. So this is negative infinity over infinity, which is one of our original indeterminate forms. So that means we can just derive both the top and the bottom. So let's go ahead and do that e to the limit as x approaches 0 from the positive. Ln x goes to 1 over x. 1 over x goes to negative 1 over x squared. Well, let's just rewrite this to make it a bit more clear that e to the limit as x approaches 0 from the positive, 1 over x divided by 1, or negative 1 over x squared is just 1 over x times negative, or I'll put the negative in front of the first one, times another 1 over x. So let's cancel our 1 over x's. We get the limit as x approaches 0 from the positive of e to the power of the limit, we get e to the limit as x approaches 0 from the positive of 1 over negative 1 over x. This is just e to the limit as x approaches 0 from the positive of negative x. That's e to the 0, and that's 1 once again. So not very exciting results, but very exciting that we figured out how to use L'Hopital's rule in 5 more situations. So thanks for watching. I hope this helped. I'm not sure if a lot of people actually learn this in Calc 1. I know for sure that I did not learn it in my high school Calc 1, but I was very thrilled to learn it in University Calc 1. I think it's very cool. So thanks for watching. I hope to see you in the next one.